Alright, good morning, good afternoon, good evening class. This is Mr. Arocena, and on today's video we're going to be talking about the concept of weightlessness. So the last video in this series we talked about universal gravitation. Today we'll talk about how you can feel weightless without actually losing mass. Alright, so before we start, let's redefine what weight was. So weight, in Physics 11, we defined this as the force of gravity on an object. Okay. And based on that definition, the force of gravity from our early studies of physics was defined as mass times g, where g, so this g, was our gravitational field strength. I think I might have mentioned it is also known as acceleration due to gravity. Okay, so both are actually interchangeable, but they mean slightly different things and have slightly different units, but they're basically the same. All right, so the force of gravity, or the weight of an object, is determined by its mass. So the more mass, the more force of gravity is acting on it. And I made a very big distinction in Physics 11 that mass and weight are not the same, because weight is force of gravity, whereas mass is the amount of matter that the object has. They are directly related though, right? So the more mass you have, the more force of gravity is exerted on you. And similarly, the less mass you have, the less force of gravity is exerted on you. Okay. Now, according to our formula from the previous video of universal gravitation, the only way for an object to be completely weightless is to be at an infinite distance from every other object. So this here, so at infinite distance, so if their separation distance is infinite, then the amount of force that gravity exerts is equal to 0. So obviously this actually won't work because you can't get infinitely far from any other object. I mean, like, even in the depths of space, you are still at a finite distance from some other mass that's out there. Okay. So then how do you feel weightless? Why do you feel weightless? Okay. Well, this comes because if you think back to Physics 11, and I guess earlier this semester, if you are sitting on a surface like so, and you have gravity acting down on you, okay, why do you feel the force of gravity? What has to occur to prevent you from falling through that surface? Now, if you answered with an upward force, you'd be correct, and in this case, it would be a normal force. So, in order to feel the force of gravity, there has to be something exerting an equal amount of force to counteract the gravity, okay? So you can feel weightless if this happens to be 0. So if the normal force of the surface is equal to 0, then you don't feel the force of gravity. You'll know you're being pulled down, but nothing is exerting a force to counteract gravity, so you don't actually feel gravity. Okay, but if you're on a surface like so, the surface will exert a force against gravity, and that's the actual force you feel. Okay, so apparent weightlessness, this can occur in, I guess, two basic situations. One, there are no supporting structures around you, so there's nothing exerting a force on you outside of gravity. Or the second situation is whatever your supporting structure isn't exerting a force on you. There's no normal force. Okay, so this is a case of no normal force. Okay. Now, both of these situations do occur on a fairly regular basis. Like, for example, this one, if you really felt like it, you could experience this by simply walk off a height. So walk off some height, and as you fall, but not when you hit the ground, but during your fall, you feel no force of gravity, because there's nothing supporting you. There's no reason for you to feel a force that is the same as your force of gravity. So if there's no supporting structures around you, force of gravity will cause you to fall down, but you don't actually feel anything because nothing is counteracting that. So you might feel a sensation of falling, but you don't actually feel the force of gravity. That is until you hit the ground. When you hit the ground like that, the force of gravity, then you suddenly feel a massive normal force when you hit the ground, like so. Okay, so that's kind of like why it hurts when you fall, because the ground counteracts the gravity. Now, the second situation, where you'd have, let's get rid of all the ink, where the supporting structure exerts no force on you. Basically, if you are standing here, here's a surface. If this surface is not moving, then it'll exert a normal force on you. But as soon as this, if the surface accelerates, this will change. This changes, the normal force. So if this surface were to accelerate downwards, your normal force, doesn't need that, but your normal force would change. And similarly, if the acceleration were to go upwards, the normal force would also change, because there's another force acting now. So the platform is accelerating, so it's going to exert some kind of net force in either direction. Okay. Now we'll talk about this particular situation with this example. So if you've ever ridden an elevator, and this is most noticeable right at the start of the elevator motion and right at the end of the elevator motion. Okay, so when the elevator goes down, the forces you feel are going to be as follows. You've got your force of gravity going this way, and then you've got the normal force of the floor exerted this way. So when the elevator goes down, and you have an acceleration going down. Normally, if the elevator is not moving or has zero acceleration, your normal force is equivalent to the force of gravity. Now, as soon as you start accelerating, you now have a net force, which will be given by the following: Newton's second law, mass times acceleration. And looking at the two forces here, your net force is really just going to be a sum of the normal force and the force of gravity. Now, taking this into account, we'll just substitute the mass times acceleration into here. So net force is mass times acceleration, which is equivalent to normal force plus mass times g. Now, given that g is going to be in the downward direction, I'll make this negative. And we can see that the normal force is going to be mass times acceleration minus mass times negative g, which when they simplify it ends up becoming mass times acceleration. The two negatives will become a positive plus mg. All right, there we go. All right, so there's my normal force is equivalent to the mass times acceleration plus the mass times gravity. Now, in the downward motion, acceleration is negative. Acceleration is negative in the downward motion, so it goes to reason then that the normal force you feel is going to be less than the force of gravity, because if you look back at our equation for calculating normal force here, if my acceleration is a negative number, this sum will basically be force of gravity minus the mass times acceleration. So my normal force actually ends up being smaller than the force of gravity. Okay, and this is why when you accelerate, or when the elevator starts moving down, you feel slightly less weight, because the normal force that the elevator exerts is actually slightly smaller. Eventually, the elevator will stop accelerating, and you'll get a situation where you have zero acceleration, and then at that point, your net normal force is just going to be equivalent to mass times g, or equivalent to gravity. Okay, so when the elevator, if the elevator is long enough, or the elevator rides long enough, eventually you start feeling your normal weight. Now for the elevator accelerating upwards, we can basically use the exact same equation. So the force analysis is basically the same. So we'll just draw the diagram. So again, you have your normal force of the floor, you have the force of gravity going down, and when we do the analysis, we get the same thing. So my net force is still going to be mass times acceleration, and it turns out that my net force is equivalent to the normal force plus the force of gravity, and we get to basically the same equation we had previously, where the net force is the mass times acceleration minus mass times gravity, and as a result we get Fn equals mass times acceleration plus mg. Now the difference here is that since I'm accelerating upwards, acceleration is positive. So what this means then is that my net force is going to be greater than the force of gravity. You can sort of see it here. If this number here is a positive number, we're adding it to the force of gravity, so my net force ends up being bigger than the force of gravity. And again, you'll feel this if you're in an elevator. Just as it starts to move upwards, you have that sudden lurch and you feel a little bit heavier just at the very beginning. And then eventually when the elevator steadies out and stops accelerating, you feel normal again. Okay. So there you go. So there's the force analysis to show that the normal force that the floor exerts is greater or smaller depending on which way the floor accelerates. So if the floor accelerates away from you, you feel less force or less normal force from the surface, and if it accelerates towards you, you feel more normal force than you expected. All right, now here's another one that some of you might experience in the future, and this is if you were in space. Now space is not devoid of gravity, but you can feel apparent weightlessness, and this is actually how astronauts can train on Earth for apparent weightlessness in space without actually going into space. All you have to do is make it so that the astronaut or the person and whatever they're in are accelerating to the Earth at the same speed, or not same speed, same acceleration. So we'll make a note here, acceleration. Okay, and I'll go back to the equation we talked about previously. So in the previous equation, we showed that the normal force is equivalent to mass times acceleration plus mass times gravity. Okay, now, if my acceleration is equivalent to gravity, okay, so if my acceleration is equivalent to gravity, then that means that Fn will be basically negative mass times g plus mass times g. So my normal force will be to 0. So if my acceleration is equivalent to my gravity, then it will end up being having 0 normal force. Okay, and that's how you can feel apparent weightlessness. So for astronaut training, what they would do is put them up in an airplane, and they would dive the airplane so that it has a downward acceleration equivalent to the acceleration due to gravity, and then the people inside the airplane would feel pretty weightless. Okay, it all comes down to the spaceship not exerting a normal force on the astronaut. Okay. So that's all you need to do to feel weightless, is to reach a situation where you feel no normal force. Okay. Here's another one that probably many of you have experienced, is if you ever take a jump on a motorbike. Okay. At some point in the flight, if you take the jump, both the rider and the bike will be falling at the same rate. Okay, they have the same acceleration due to gravity. There's nothing acting on them. So there's no normal force being exerted by either on the other. So both objects would appear weightless. Okay, and it's like I said earlier, is that if you really want to feel weightless, just walk off a height of some sort and you can feel weightless. Okay. Obviously don't walk off anything too high, otherwise you might seriously injure yourself. Okay, but if you like stand on a table and walk off that brief moment before you hit the ground, you will feel weightless. Okay, until you hit the ground, in which case then you will feel all your weight, because the ground would exert that kind of gravity against you. Right. Now, if you are a little more adventurous, I suppose, you can experience this in a vehicle. And this is kind of what happens in roller coasters. So if you are in a car and you're going over a radius of a hill, okay, and this is, I think there's one road nearby where you could experience this. Some previous students told me about this, where you have a very hilly road. And if your car is driving over that road, that car looks terrible, but whatever. If you are traveling over it fast enough, you can actually feel weightless as you come cresting over the top. This is a common tactic for a lot of amusement park rides, where you go up and down a lot. Coming down, you can feel quite weightless depending on how quickly it's moving over top of that hump. All right, now the calculations here are actually quite simple, because again, from the previous example 2, I think, example 2, we show that as long as your acceleration is the same as gravity, the negative sign is kind of redundant, but as long as it's the same as gravity, then you should feel no normal force acting against you. Okay. So let's do the calculation to get that. Okay, so our goal here is to make our normal force equal to 0, and the easiest way to do that is to make it so that our acceleration is the same as gravity. Okay. All right, so going over top of the hill, we have two forces acting against us. We have centripetal force, mass times v squared over r, and then we got the force of gravity on the vehicle, which is mass times gravity. And then our goal is to make the normal force equivalent to 0. Okay, so basically we want our centripetal force to be entirely provided by the force of gravity. Okay, because if I analyze my situation at the top, I have normal force, I have gravity, and my centripetal force is going this way. So our centripetal force ends up being kind of our net force, because we want to keep it going around the circle. And the normal force, we want to reduce that as much as possible. So in order for this to happen, in order for normal force to be completely neglected, we have to ensure that the centripetal force is equivalent to the force of gravity. And we can do this, we set the equations equal to each other. mv squared over r equals mg, like so. The masses cancel out, so you can do this no matter how big or small your vehicle is. And we can set the following: v squared equals g times the radius, and then we'll just square root it to get rid of the square. All right, so our total speed then, if I want to go through this, let's see, gravity is 9.8. We have a radius of 20 meters, and then we'll square root this. 14 meters per second. So if we have a hill of 20 meters of radius, and we travel over that hill with a speed of 14 meters per second, then you should feel apparent weightlessness at the very top of that hill as you come cresting over. Now 14 meters per second is actually kind of tame. I think 14 meters per second is around 50 or 60 kilometers per hour. It's not so bad. But a 20 meter radius hill, I think, is also really small. So if the hill is larger, so if the radius of the hump is larger, you'll obviously have to travel faster over top of that to feel weightless. Roller coasters are really good for this. If you've ever ridden a roller coaster, as you come down a hump, depending on how fast you were going over the hump in the first place, you could feel quite weightless. All right, now your assignment for this particular section then, if you have your textbook, is as follows. And a reminder that if you want to be weightless on Earth, your centripetal acceleration must be the same as the gravitational field strength of the Earth, or effectively, the centripetal force has to equal the force of gravity. This is important because I think there's a question that mentions how fast do you have to spin the Earth in order to make everyone feel weightless at the equator. I think that's one of the questions. Anyways, but there you go. Alright, if you guys have any questions, you guys know how to get a hold of me.